Okay, which brings us to Act 2. Don't write your own parser. And definitely don't write your own programming language. Or smart contracts were a terrible mistake, and we need to burn it all with fire. I forgot to mention at the beginning of this talk, the audience for this talk, it is going to be both like defensive and offensive cybersecurity people. I don't expect there to be any blockchain specific people there, so I'm going a little bit high level with this. So first, what does crypto mean? Hey, everybody with me. Crypto means cryptography. Or cryptozoology, that's also cool. What is a blockchain? All a blockchain is an immutable public ledger. So Alice has $10, Bob has $5. If Alice gives Bob $8, then that means Alice has 2 and Bob has 13. So if Alice comes along and tries to give Eve $10, then Eve can inspect this public immutable ledger and see that, oh, Alice only has $2 right now, so I'm going to reject her offer to give me $10. But you can put anything on a blockchain. It's funny to think that the cryptographic validity of the Bitcoin blockchain is predicated on an ASCII art picture of Ben Bernanke that Travis Goodspeed and Dan Kaminsky put onto it. Because you can put anything on a blockchain, even code. Which brings us to smart contracts. So before I explain smart contracts and how you put code on the blockchain, I want to talk to you about this awesome currency that is almost completely anonymous and untraceable. And it's really easy to use. It's super quick. So Alice can just give like cash to Bob, and it's like instantaneous. It's amazing. In contrast, smart contracts, you have code on the blockchain, immutable, in the form of, in the most popular smart contract platform, Ethereum, code in the form of the EVM bytecode, which is a stack-based virtual machine. So Eve, if Eve wants to interact with that code and perhaps have that code send her cryptocurrency forward to Bob, she can send some cryptocurrency along with a transaction in the form of like a function call to the blockchain. Then a bot, or otherwise known as a miner, can choose to take her transaction and execute it against the code. And in return for executing it, and taking its time, and as an incentive, the miner gets a portion of the cryptocurrency that Alice sends along. But then Eve can observe all of this happening. She can see that Alice submitted this transaction because it's public. She can see all the code on the blockchain because that's public. And Eve might discover a bug in the contract and send another transaction exploiting that bug and taking Alice's cryptocurrency away from Bob. And all of this happens in such a long amount of time that I couldn't even fit it into the stopwatch emoji. Nobody wants to write raw EVM bytecode or EVM assembly. So various languages were created, high-level languages were created to make it easier for developers to deploy these smart contracts. The most popular of which is called Solidity. So I went ahead and went through the programming language checklist for Solidity. It is a new object-oriented procedural stack-based statically typed language. And the creators of it made some debatably terrible design decisions in the language. There is very little documentation, and what documentation is out there is not consistent with what the compiler will actually do. And the people who created this language and its associated tools or tool chain had never created a language before, let alone written a compiler. Also, they based the syntax of the language on JavaScript, which I shouldn't have to tell you maybe isn't the best. That doesn't give you the warm and fuzzies about a platform that you are going to be trusting with hundreds of millions of dollars of cryptocurrency. So in summary, yeah, not a good language. So let me give you an example. What do you think this code will do? Which case will this code go into? I'll give you a clue. Most major languages will go into the first case. So of course, Solidity will go into the second case because of operator precedence that doesn't match what most other languages use for operator precedence. As another example, let's take a look at this relatively innocuous looking for loop. So let's say foo.length is like thousands long. And we want to know, what does foo element 1337 look like after this for loop? Does anybody know? I know some of you know because we've talked about this before. All right. So the issue here is that since the Solidity compiler doesn't really do any look ahead or optimizations, and since it allows for this JavaScript style var variable definition, and since Solidity is statically typed, it needs to make the compiler needs to make a decision at this point as to what type of type it should assign to the variable I. Well, here the constant literal 0, it's going to choose the smallest type possible that can represent 0, which is going to be a uint 8. So then it's just going to assign I to be a uint 8, which means that every 256th iteration of this for loop, it's going to overflow I, and I will wrap around back to 0. So all of the elements in foo past 255 are going to be uninitialized. Recently, for a project, I needed to write a parser for Solidity. There is one reference implementation. There is basically one reference implementation for Solidity, which is the parser inside of its compiler, Sol-C, which is written in C++. And there is also a JavaScript implementation, which I believe was automatically generated using mscripton from the C implementation. I wanted to do everything in Python, and so I figured, well, let's just look at the documentation, and sure enough, they have an EBNF grammar. So okay, great, I can take that grammar, I'll stick it in a parser generator, and then I'll be able to parse it in Python. No sweat. Well, I struggled to get a parser generator to accept that grammar. So you inspect it a little bit more, and you discover that the grammar isn't correct. Not only is it context sensitive, and do they have like regexes sprinkled in everywhere, but it's actually ambiguous. So the Solidity compiler and its associated parser are open source. We can just go on GitHub and look to see how they did it. What parser generator did they use? Well, if you actually look at their source code, it turns out they didn't even use that grammar. They coded up their Solidity parser entirely by hand from scratch. So this is partially the reason why we have those operator precedence issues. In fact, there's an academic paper that was published recently about how hard it is to parse Solidity. And this paper is pretty rigorous and goes through their grammar and explains why it doesn't work and all of the things they had to do and hoops they had to jump through to create an parser the correct way for Solidity. So for example, they have a comma operator, which is completely ambiguous, and there's no way to represent that in a context-free grammar. Moreover, ignoring all the parsing stuff, even if the parsing was correct and rigorous, the compiler itself does barely any optimization or look ahead. It will emit all sorts of operations that should have been optimized out, like doing exponentiation on constants. In fact, a recent study discovered that the vast majority of operations that are performed on the Ethereum blockchain are the exponentiation operator of constants due to this terrible compiler. This is costing people money because remember, when you execute a transaction, you have to pay a miner its incentive fee to execute the code for you, which is a function of which and how many operations it has to execute. Speaking of exponentiation, a couple weeks ago, there was a patch to the compiler to deal with exponentiation. If you look at the comment here, it's like, what? Do they even understand how exponentiation works? And this actually resulted in a high severity vulnerability where using the exponentiation operator in Solidity on a type shorter than 256 bits can result in unexpected values, or because basically the compiler was screwing up. All of this has happened before, and it will happen again. So they are proposing a new intermediate representation called Yule with the intention of doing more compiler optimization on this intermediate representation, similar to how Clang uses LLVM as an intermediate representation, which is a great idea, and that's what pretty much all modern compilers do. But first of all, Yule doesn't implement single static assignment, which is what all good modern compilers do, because that representation makes all of the optimizations much simpler to do. Moreover, the grammar for Yule is really jacked up. If you notice, the if production rule is never used. The default switch case isn't followed by a colon, even though in all of the example code, you have default colon, just like in most other languages. Switch foo is a legal production in this grammar without any cases or defaults. So what would a Yule assembler do or compiler do if it just had a switch statement with no cases or defaults? We don't know. That's legal in the grammar, though. And string literal can't be represented without casting, even though it is in the example. So it's clear that, once again, they are writing the parser from scratch and generating the grammar as an afterthought, not actually generating the parser from the grammar. So what can be done? Buy our free open source tool products. We have an open source tool called Manticore, which is a symbolic execution engine that supports EVM. So you can execute a contract and simulate transactions to that contract and query and say, is it possible for this variable to be equal to this value at this point in time, and Manticore can tell you whether or not it's possible, and if so, what are the transactions that that can make that happen. We have a static analysis tool called Slither, which will find the majority of common Solidity bugs. Echidna is a property-based fuzzer for EVM. Rattle is an EVM to a single static assignment lifter, so you can actually do all those analyses that single static assignment gives you. Atheno, which will be released in a couple weeks at TruffleCon, is a test framework integration tool to allow you to more easily use Manticore and Echidna with existing smart contract code bases. We have a number of other tools, an EVM disassembler, we have a bytecode analysis framework, and a bunch of other resources if you are a smart contract developer that you can use to increase the security posture of your code base. So in conclusion, files have no intrinsic meaning. Polyglots aren't just a nifty parlor trick. You can make them too. Always open PostScript in a virtual machine. PDF is broken. Smart contracts are more broken. Don't write your own parser. Definitely don't make your own language, and buy my product. As homework, if you're interested in this polyglot stuff, check out Packer GTFO 16, which was 3 issues ago. And its polyglot is a Kaitai struct web server that when you navigate to it, it will give you an interactive hex editor where you can reverse engineer itself and play around with the guts of the polyglot. Lots of acknowledgements here. On the left-hand side, that's the all of my collaborators for the polyglots on Packer GTFO from Act 1. And on the right side, all of my colleagues at Trail of Bits who helped out with various portions of Act 2. So thanks a lot. And are there any questions?